In one of my previous talks, I defined infinite series, mostly series of real numbers. So, and we have seen that the most important question that one can ask about an infinite series of real numbers in this case is whether the series is convergent or divergent. Now, sometimes it is very easy to see whether a series is really converging to a particular value. It should be finite value, but sometimes it is not. In most cases, actually, it is we need to do something in order to find out whether the series is convergent or not, and if converging, if it is a convergent series, to what value it is converging. So it would be really nice if we have some technique, maybe some theorems or some results, which will immediately tell us, or maybe after a little bit of manipulation will tell us whether the series is really convergent or divergent. That would be really a great thing. So today I am going to discuss two such very important what is known as tests for convergence, tests for whether and which will determine whether a series is convergent or not. And after that I will just give the definition of a very important series which is known as power series. Now, power series has immense application in various fields of analysis, probability, stochastic process, and so on. So, but today we will restrict ourselves only to defining the power series and little bit of concept about its convergence. But note that the convergence of power series can also be tested using the tests that we are going to discuss. So, today's discussion starts with, as we have already mentioned, the series or infinite series of real numbers, but today we will mainly focus on various tests or various techniques to check whether a series is convergent or not. So, we will first define the test for convergence, a little bit of recapitulation on series. We will explain or discuss two important tests. One is root test, another is known as ratio test. Of course, we will discuss few examples, and then we will define what is the meaning of power series and how one can see the convergence of this power series. So, let us first consider an infinite series a1 plus a2 plus dot dot an and so on. For the sake of simplicity, we first assume that all these an's, that is a1, a2, an and so on, they are all real numbers. We define a partial sum Sn as a sum of first n numbers in that series, that is summation k equals to 1 to n ak. Now, it is clear that given any n, we can always define Sn in terms of the terms in the infinite series. So, Sn can always be treated as a sequence, and since Sn can be treated as a sequence, so everything, all the results, all the theorems that we have already studied or we have already known regarding the sequence, we can apply those theorems, those results to this particular sequence, which is Sn, which in fact gives the idea of the infinite series. So, in other words, convergence or divergence of a series can be studied in terms of convergence or divergence of the sequence Sn, that is sequence of partial sums. So, first recapitulate one important test that we have already done, which is known as comparison test. Suppose modulus of the nth term in the series, that is modulus of a n less than equals to c n for some n greater than n naught, that rather for all n greater than equals to n naught. N naught is some fixed positive integer, and if summation c n converges, then it can be shown that summation a n also converges. That means here convergence of the original series is studied in terms of convergence of a series which is where each nth term of the new series is dominating the nth term of the original series. Similarly, we can also think of the same kind of test, but to find the divergence of a series. That is, if a n greater than d n for n small n greater than equals to capital N naught, where capital N naught is some fixed positive integer, and if summation d n diverges, then summation a n diverges. It is important to mention that here we consider only the non-negative terms of the series that consist of non-negative terms. So, these two theorems actually will be used subsequently in order to prove the two main theorems, rather two main tests that we are going to discuss today. So, first one is root test. This test is due to Cauchy. So, consider the series summation a n and let alpha is lim sup as n tends to infinity, lim sup of modulus of n whole to the power 1 by n. That means nth root of modulus of n. and consider the limb soup of that sequence. Then summation n converges if alpha less than 1 and summation n diverges if alpha greater than 1. So, the natural question will arise that what happens when alpha equals to 1. Unfortunately, the test will be inconclusive. That means we cannot take any decision whether the original series summation n converges or diverges if we get the value of alpha to be equal to 1. However, if alpha less than 1, that will definitely conclude that summation n converges. On the other hand, if alpha greater than 1, that is strictly greater than 1, then we can say that summation n diverges. Let us prove this theorem. First, consider alpha less than 1. Now, since alpha less than 1, there always exists, alpha is the limb soup of modulus of n whole to the power 1 by n. So, there always exists an integer capital N and beta where alpha less than beta less than 1 such that modulus of n whole to the power 1 by n is less than beta for all small n greater than equals to n naught. Then, for small n greater than equals to n naught, this will imply that modulus of n less than beta to the power n, because modulus of n is always positive. Now, 0 less than beta less than 1 implies beta is a positive fraction. So, if we just consider the summation of modulus of a n, that should be less than summation beta to the power n, and since beta lies between 0 and 1, this is nothing but a geometric series with common ratio less than 1, rather common ratio lies between 0 and 1, a positive fraction. So, naturally beta summation beta to the power n converges, and hence just application of the previous comparison test will ensure that by taking Cn equals to beta, the result will follow immediately. So, here the trick is that we are applying comparison test on beta, on modulus of n, and the dominated term is just beta, which is nothing but Cn in the comparative in the comparison test. Now, or rather Cn is actually beta to the power n, because we are considering the summation of Cn. So, Cn should be beta to the power n, that means the common ratio is beta. Next, we consider alpha greater than 1. Now, again, since alpha equals to limb soup of modulus of n whole to the power 1 by n as n goes to infinity, there always exists a subsequence nk such that modulus of a suffix nk whole to the power 1 by nk goes to alpha as nk goes to infinity, because it is the limb soup. That means we can always find such a subsequence. Now, this immediately imply, since alpha is greater than 1, this immediately imply that modulus of n is strictly greater than 1 for infinitely many values of n, because it goes to alpha as nk goes to infinity. Now, we know that summation n, the convergence or divergence of summation n can sometimes give some indication, some idea about the nth term. So, we know that summation n converges, that will always imply that the nth term goes to 0 as n goes to infinity. This is always true. Whenever we have converging series or rather convergent series, nth term will always goes to 0 as n goes to infinity. So, there is a contradiction, but here since modulus of n greater than 1 for infinitely many values of n, it cannot go to 0 as n goes to infinity. So, there is a contradiction, and hence the result follows immediately. But we have claimed that in the theorem that alpha equals to 1 test is inconclusive. That means we are not definite that whether the series is convergent or the series is divergent. In fact, we can give example that in one case when alpha equals to 1, the series is convergent, while in another case the series is divergent. So, we cannot prove this, but we can give examples to indicate, to imply that the test is inconclusive when alpha equals to 1. So, consider two series. One is summation 1 by n equals to 1 to infinity, and the other is summation 1 by n square n equals to 1 to infinity. Noting the fact that we know already that limit n tends to infinity n to the power 1 by n equals to 1, we immediately see that alpha equals to 1 for both the series. But it is clear first series diverges while the second one converges. Because we know that 1 by n summation of that is a divergent series, and 1 by n square sum over that is convergent. So, for alpha equals to 1, we get two different series, one is convergent, another is divergent. Let us now consider the next test, that is D'Alembert's ratio test. So, again consider the series summation a n. Now, this summation a n converges if limb soup as n goes to infinity modulus of ratio of two consecutive terms, that is n plus 1 by a n less than 1, and diverges if this ratio modulus of a n plus 1 by a n is greater than equals to 1, for all n greater than equals to n naught for some fixed integer n naught. So let us prove this test or this theorem or result. So first consider that modulus of ratio, that is modulus of an plus 1 by an, lim sup of that quantity as n goes to infinity is less than 1. Then, like the previous root test, we can always find an integer capital N number beta such that modulus of an plus 1 by an less than beta. Now remember, beta is less than 1 for every n greater than capital N. So now we can immediately write modulus of, since small n greater than equals to capital N, we can always write modulus of a capital N plus 1 less than beta into a modulus of a capital N. Similarly, modulus of a capital N plus 2 less than beta into modulus of a capital N plus 1, which is again less than beta square modulus of a capital N, and so on. So in general, we can write for p greater than equals to 1 modulus of a n plus p less than beta to the power p into modulus of a capital N. So clearly, we can immediately write modulus of a small n less than modulus of a capital N into beta to the power minus capital N into beta to the power n for all n greater than equals to capital N. Again, just taking Cn equals to beta in the comparison test, we can apply comparison test. We can see that the result follows immediately because beta less than 1 and summation beta to the power n is convergent. So this proof is complete. Again, the second part, that is when modulus of ratio of an plus 1 and an modulus of that is greater than equals to 1, we can immediately show that, like the root test, the follow arguments similar to the root test, we can immediately show that n goes to 0 does not hold, because if summation n convergent, then of course obviously n must go to 0. But if we can show that n does not go to 0 or n goes to 0 does not hold always under that condition, that is under the condition where modulus of n plus 1 by an greater than 1, then we can say that the series is divergent. So now we know the two important tests which will ensure the convergence or divergence of a series. Next, we will define power series. Power series is nothing but a sequence of complex numbers. Suppose we have been given a sequence of complex numbers Cn, then the series summation n equals to 0 to infinity Cn z to the power n is called a power series. The numbers Cn are the coefficients of the series and z is a complex number. Suddenly here, for the first time, we have generalized the definition of a series in terms of a complex number instead of real numbers that we have already discussed till now. Note that z can always be treated as a real number when the imaginary part is 0. So this is a general definition of a series, or rather this is a special type of series which we call power series. This power series is very important in analysis, probability and many other branches of science. We will end today's discussion few remarks. The first one is that convergence or divergence of the series, that means of this power series, must depend on the choice of z. Next remark is that when we have a power series, we have a circle associated with this power series which we call circle of convergence. Now this means that if z belongs to this circle or z lies in the interior of the circle, then power series will converge. On the other hand, if x does not belong, or rather x belongs to the exterior of the circle, and then the power series will diverge. So this circle actually gives some idea about the convergence, and radius of this circle is known as radius of convergence. So we can propose one theorem regarding the convergence of this power series, which we call let's call it another theorem. So consider the power series summation Cn z to the power n and put, like root test or ratio test, alpha equals to lim sup n goes to infinity modulus of Cn whole to the power 1 by n. This is actually lim sup, but exactly like the root test. In ratio test also we have used lim sup, but that is a lim sup of two ratios of two numbers, and we define capital R as 1 by alpha. Then summation Cn z to the power n converges if modulus of z less than R and diverges if modulus of z greater than R. So this R actually determines, or rather the comparison of modulus of z in comparison to R, that determines the convergence or divergence of the power series. Now remember, R is actually defined in terms of the coefficients of the power series, that is Cn. Note that if alpha equals to 0, capital R equals to plus infinity, and if alpha equals to plus infinity, capital R equals to 0. So this R is the radius of convergence. So in case alpha equals to 0, that means the entire positive half, this entire length, the radius of convergence, the length of the radius of convergence is actually infinity. R is called the radius of convergence. I will end this talk outline of this proof and a few examples. Put an equals to Cn into z to the power n. Just apply root test to get lim sup of modulus of n whole to the power 1 by n is nothing but z, modulus of z into lim sup of modulus of Cn whole to the power 1 by n, which is nothing but 1 by r. That means the entire quantity equals to mod z by r. So it is clear by the root test that summation Cn z to the power n converges if mod z by r less than 1, that is if mod z less than r, and diverges if mod z greater than r. So this is just a direct application of root test that we have learned at the very beginning. And this entire convergence or divergence of power series can be explained in terms of root test, or rather in terms of the radius of convergence. So all we have to do is to determine the radius of convergence associated with the given power series. As examples, first example is that if the power series is summation n to the power n z to the power n has r equals to 0, the radius of convergence is 0, since alpha equals to lim sup of n, which is nothing but infinity, and summation z to the power n has radius of convergence as 1, of the coefficients is equals to 1. Now one interesting thing is that what happens when mod z equals to 1. Now in this case, actually this is a very special thing, and one has to look at the actual power series when mod z equals to 1. So in this case, if mod z equals to 1, it diverges as z to the power n z does not tend to 0 as n goes to infinity. And the third example, as summation z to the power n by n factorial, this as r equals to plus infinity. So this radius of convergence gives some idea about the nature of the convergence of the power series. So today I have discussed two important tests. One is Cauchy's root test, and another is ratio test, which is due to D'Alembert. So these tests actually ensure in most cases whether a series is convergent or a series is divergent. And it is important to see that these tests are in terms of the individual terms, or rather the nth or maybe n plus 1th terms of that series. So here the convergence is ensured through the properties of individual terms, most importantly nth or n plus 1th terms. And later we see that there is another important series which is called power series, and this gives us an indication. Here we have defined, although previously we have defined series only series of real numbers, but power series we have defined in general, that is power series can be defined in case of complex numbers also. So that immediately suggests that we can also extend the entire concept, entire theorems, all the results when we deal with complex numbers in general instead of only real numbers. But of course, if the imaginary part is 0, then complex number reduces to real number, so everything would be valid for real number series. So this gives us a very good idea about how to determine the convergence or divergence of a series in terms of or using two important tests. One is root test and D'Alembert's ratio test.